It's my pleasure to introduce our speaker today for the OpenFOAM for Combustion Forum, Professor Hong Yim from KAUST. Professor Hong Yim received his bachelor's and master's degrees from Seoul National University and PhD from Princeton University. And then he conducted postdoctoral research at Stanford University and the San Diego National Labs before he moved to University of Michigan, where he held assistant, associate, and full professorship positions. And then he joined KAUST in 2013 as a professor of mechanical engineering. He is a recipient of the NSF Career Award and SAE RAV Teacher Educational Award, and has been inducted as an international member of the National Academy of Engineering of Korea. And Professor Hong Yim is also a fellow of the Combustion Institute and the ASME, and also an associate fellow of AIAA. He has also served as an associate editor for the Proceedings of the Combustion Institute and currently on the editorial board for Energy and AI. Professor Yim's research and teaching interests are primarily fundamental and practical aspects of combustion and power generation devices using high-fidelity computational modeling. Current research activities include DNS of turbulent combustion at extreme conditions, alias of turbulent flames at high pressure, combustion of hydrogen and e-fuels, spray and combustion modeling in advanced internal combustion engines, advanced models for pollutant formation and plasma-assisted combustion. Okay, please, Professor Yim.
Grab that. Yep, I think it's all good with the laser. All right, thank you very much. Thank you for the kind introduction. It's my great honor and pleasure to give a presentation for this OpenFOAM seminar series. And in fact, it was not exactly planned when I signed up, but I'm currently in Korea, so in a similar time zone at the moment, although I'm actually flying back to KAUST tonight. So, but anyway, it worked out very well. So, well, today I would like to give some overview of multiple projects that I've been working on. The common theme is obviously the use of OpenFOAM as a main tool, but it's going to be quite kind of multifaceted and a kind of different topics throughout the next hour. So the title is also kind of generic, as you can see. It's just a high fidelity simulation using OpenFOAM. Here I will talk about some spray problems and combustion problems and so on. So that's kind of the main topic. My name is Hong Yim, and for the Chinese-speaking audience, I normally like to put my name written in Chinese characters so that you kind of see, what it means. And I'm a Korean native, currently a U.S. citizen, but anyway, so my family root is from these Lim family, which is also Lam in Cantonese and Lin in Mandarin. I'm a professor in mechanical engineering, also affiliated with Clean Combustion Research Center. Before I start, I would like to acknowledge the generous sponsorship from KAUST on various types of funding sources, including baseline funding and center funding and other comparative research grant. And also a lot of this simulation work was done with the use of supercomputing facilities at the KAUST Supercomputing Laboratory. All right, let me introduce my colleagues, brilliant colleagues. We have currently a total of 10 active faculty members at CCRC, KAUST. Now, recently, I'm going to mention that in a moment, but we have added some new faces. Professor Bassam Dali, many of you know, and Dr. Shulu from he's actually not exactly a combustion person, but I will tell you more about that. And Professor Bill Roberts is the center director. Mani Sarati is associate director. We cover various, all sorts of combustion research. As you can see in this called the our CCRC regime diagram. I created many years ago, and everybody liked it, and we are commonly using it. It shows us the kind of general multidisciplinary and multi-scale nature of combustion research, starting from molecular level chemistry to flame study using direct numerical simulation that goes into device level, then a laboratory scale large eddy simulation, and that builds up into the device level engine simulation. And every step of the way we collaborate. My work covers these three sections: DNS, LES, and device CFD part. And each step I work closely with the experimental counterpart within CCRC and many other external colleagues. Here's my group, which has grown quite big now. It's so about, well, it's still a moving target. I have recently graduated a few, and some of the postdocs left, but it's a fairly big group. The names highlighted in red are the ones who really contributed directly to the material that I will be presenting today. Those are Francisco is my research scientist. Alberto and Lorenzo and Suleiman are all PhD students, and a few of them are soon to be graduated. All right. So again, I'm unfortunately and fortunately the only CFD person in the center, and given the diverse research activities, I get to do all sorts of simulation activities, starting from DNS and LES and the engine work. So DNS, I usually use my own research code, in-house code called KAUST. And the engine simulation, we are heavily using Converge, the commercial code. And the device level large eddy simulation is mainly conducted using OpenFOAM research tool. This is something I have started working on since I joined KAUST about 10 years ago. And this has become one of the integral part of my research activities. So that is about, I'm gonna only talk about, not necessarily all LES, there are some DNS component as well, but OpenFOAM related simulation work will be presented today, okay? I think I realize I have prepared a little too many slides, so in the interest of time, if the time is limited, I will just skip ahead, right? So that's the idea. Well, just to set the tone, I'm sure we're all in this audience is easy to convince. I don't think I need to spend too much time on it, why we are working on combustion research, but just to set the kind of current, the status is that I guess if this is an example of a EU is trying to, the legislation is shifting back into starting to recognize that the battery and solar energy is not going to solve 100% of the problem. They are trying to acknowledge the gases and the nuclear to be included in the green in their taxonomy. Well, so I think my point is that I think the entire world is beginning to realize that such a rapid push for a green solution is probably not realistic. And we also clearly know the solution. So I think, especially I'm speaking to the younger audience in this crowd today, who are kind of doubtful about their future. My personal opinion is that I think there are plenty of many exciting work that is needed, especially to deliver the solution toward the energy sustainability in the many decades to come. So, well, Saudi is in fact one of the forefront in pursuing this green, sustainable energy. As one of the major petroleum producer, this was a remarkable move. So this has been going on for a few years now. They have the keyword called circular carbon economy. So as I think the story is self-explanatory if you look at the picture here. So they will use some hydrocarbon for now, but in the long run, it will be replaced by solar energy. And then with that, we will produce hydrogen, and that can go into other additional synthetic hydrocarbon fuel, and so on. So these are some blue letters, are some of among the many research topics, related to many of these research portfolio. These are some of the things that we combustion researchers current can contribute in the future. So there are many work to be done. Well, so I guess our vision toward the eventually, if we stop using petroleum, how is the combustion relevant? I guess the idea is that solar will be the solution. There's no question about that. It's going to be the major key enabler, because it's ample, just a sheer amount of energy available through the solar system is huge. And then using the electricity, and we will produce hydrogen, and that itself is a good fuel, or with some issues with the storage and the safety issues. So taking a step further, we can produce additional hydrocarbon or carbon neutral fuels like methane and ammonia and so on. And even additional chemical steps can produce e-gasoline and e-diesel types of and realistic engine fuels. So these are the whole category of e-fuels. I think this is a context that not many people realize in the general public. I think it is our job as a combustion specialist to go out, reach out to educate the public about the actual e-fuel not as a competitor against petroleum, but it is actually a complementary idea about as a energy storage and transportation. So this is a really important thing to develop and utilize. So with that in mind, the current CCRC at the Combustion Center, our research forecast is exactly that. So we basically recognize there are some industrial sectors that are difficult to immediately decarbonize, such as heavy duty, marine, and the other power generation. And also there are a lot of industrial heat that cannot be easily generated without combustion. And the storage, transportation, and utilization will become big, significant issues. And these are going to be the wider variety of research activities we will be engaging in the next decades to come. In doing so, especially for me as a the computer's application, we will directly employ a lot of these modern AI and machine learning techniques toward the improved computational capabilities, as well as diagnostics and so on. So these are some of the ongoing themes that we are trying to adapt. Compared to 10 years ago, we have changed our research direction. So some of the new research direction we are working on is, number one is definitely e-fuels. So especially hydrogen and ammonia are the two key the fuels. I guess I don't have to emphasize this to this audience. Everybody knows that. And in fact, maybe the great majority of the combustion community has moved into these ammonia hydrogen combustion research. So with that, and then that with the marine transportation particularly in mind, I think ammonia in marine transportation is commonly accepted. I think it's all the community has agreed that it will be the main way to go with the sustainable marine application. And some other interesting topic which I won't have time to discuss today, it is carbon capture issues. We are working on it. And Professor Bassam Dali is also bringing in a new area of research, such as concentrated solar power, solar thermal kind of applications. Not exactly a combustion research, but we are working on that. And as I mentioned earlier, Dr. Xu Lu, he's a junior member. He is actually working a lot on catalytic conversion to produce hydrogen and various other aspects, so including some fuel cell activities. So while I emphasize significant importance of combustion as a critical enabler, we are also recognizing the increasing interest in the various other means of power storage and transportation and utilization. So we are, in fact, the CCRC name itself is subject to change, which we are kind of slowly considering. All right. So with that introduction, in the next maybe 30 minutes, I will divide my talk into 3 main parts. Again, I don't intend to go into too much of a detail, just to give you a glimpse of a brief idea what kind of work I'm working on using OpenFOAM, which is a powerful tool. And in the hope that maybe this will attract some interest from other people in the audience. And we are hoping to develop some potential collaboration in the future. That's the main idea. I think I need to. I think this one works better. All right. So the first topic is ammonia spray using OpenFOAM. This is more like a DNS, in a sense that gas phase is DNS and Eulerian and Lagrangian spray model. And then second topic is going to be turbulent ammonia flames, jet flames. It's a LES application. The focus is about developing combustion submodels like flamelet and so on, and with the combination of machine learning. And final topic is a multiphase application using volume of fluid methods. We are trying to solve the droplet, the spray, the breakup. And the second half of this part will be about droplet, single droplet deformation and breakup physical processes. I think these 3 topics are kind of complementary and kind of intentionally set up such a way that the first DNS topic is more about physics discovery. We want to learn the fundamental physics by running high fidelity simulation. Second topic is more focusing on developing combustion submodels to be able to run turbulent combustion. It's a standard. Many of the turbulent combustion community is working on that, and this is a part of that effort. Final part is actually reproducing very, very complex, intricate physics by using state-of-the-art computational algorithms to resolve all these multi-phase and multi-component flow physics. So I hope I will entertain the audience for the next 30 minutes. All right. So the first topic is ammonia spray DNS. Main contributor is my student Lawrence Angelilli, who also works closely with my colleagues at University of Rome, Pietro Ciotoli and Professor Mauro Ballorani. So, well, again, ammonia is a big topic today, obviously. And ammonia is present in the liquid phase most of the time at the typical atmospheric condition. So it's easy to carry, just like LPG. But when it comes to burning them, well, you can preheat it and have it as a gaseous burning. Or if that energy uptake is a little bit of a concern, people are also considering direct injection into the combustion system and burn it like a spray flame. So, but there is not much work done about characteristics of ammonia spray. So we want to investigate that. So this was our first step toward the enhancing understanding of our fundamental characteristics of ammonia spray. What do I mean? I mean, ammonia spray is just like, it's similar to ethanol, but it's even more so. It's because it's got a large latent heat. So there's a strong presence of evaporative cooling effect. And the saturation temperature is also very low. So there are some potential possibility of the flash boiling or some other unique physical characteristics may be expected. So our main objective here is to run some basic direct simulation, Lagrangian Eulerian simulation, to understand the spray dispersion evaporation pattern and how is it different for being ammonia. So that kind of simulation is done using OpenFOAM. As you know, the spray foam is a very nice starting template we used, and this is a general configuration. I don't want to read all the gory details of it. So basically, we have a periodic pipe attached here, so that has a fully developed turbulence generated at the inlet, and along with it, we are injecting the liquid droplet, ammonia droplets, in a Lagrangian particle fashion. So a large number of ammonia particles are injected at the droplet temperature of 220 K. And then the main parametric study here is that we explore different ambient temperature. One is the same temperature as droplet, and second, two other cases was heated about room temperature and sufficiently high temperature. And the gas velocity, the environmental velocity is quiescent, although there is a turbulence inflow coming in to carry the ammonia spray. So here are the quick snapshot images of the black dots represent the ammonia. Individual dot is a single droplet of ammonia. And you can clearly appreciate the gas temperatures are going up. As you can see, the color map indicates the background gas temperature. And there is a clearly sign of evaporative cooling in the core region due to the ammonia evaporation, and it gets heated up. So the clear contrast here is the dispersion pattern. So cold one, of course, evaporation is slow, so you have ammonia, the droplet reaching out all the way to the downstream. But at the same time, the clustering is present in the heated environment. So those are this kind of typical evaporation, evaporative cooling, and dispersion pattern is the main subject of study. So taking further analysis, we are looking at the droplet, how the droplet size drops down as we move downstream. So it's kind of confusing figure, I understand. So for the solid lines are the cold environment, and the dashed line is a 300 K environment, and dotted line is a high temperature condition. So clearly, high temperature environment, the droplet evaporates quicker. So the length of this the droplet, the liquid jet penetration gets shorter. And having said that, but actually we were able to find some self-similarity, where by scaling this initial droplet diameter, 50% of the initial droplet diameter, which is R50 here, if we scale all those physical scale by that, those three patterns are kind of collapsing onto each other. So that was a kind of a unique, interesting finding. Well, continuing on how the exact temperature distribution for the droplet, as well as the surrounding gases. The left half is a droplet temperature distribution, and right half is a gas for cold, medium, and hot environment. Obviously, for hot environment, it gets heated more. In the cold environment, actually drop temperature goes down because it's not heated up by the environment. This is a clear sign of the evaporative cooling. While if you have a little bit warmer the gas phase, and you can see the droplets are getting slightly heated up and then evaporated. Still some initial drop of temperature is present because surrounding gases are not high enough. And when you have a hot temperature of 600 K, you will see much more rapid gas temperature rise, and therefore the droplet temp is also evaporated. But droplet temperature doesn't seem to increase much, while the evaporation happening is much shorter. So just to elaborate a little bit further, now this picture tells us more about actual mass and enthalpy source, which really represent the action of the evaporation. So when you have a cold environment, there is the most active evaporation going on at the surrounding the periphery of the jet, and the mixing, basically the mixing layer line. In the meantime, the blue color of the enthalpy source, which is a negative, that means clearly the sign of evaporative cooling, as I mentioned earlier. And that evaporative cooling effect is still visible for a warm environment like a room temperature condition, which is absent when you heat it up to 600 K. It becomes much shorter and it is intense evaporation. So everything looks reasonable, and the key signature of this ammonia sprays, as we expected, there is a strong, the latent heat effect is you have to really heat up the ambient to prevent that evaporative cooling effect. That's the key observation. Well, one of the final the key interest was about the dispersion pattern. So you may have noticed earlier about some the clustering effect going on. So it is a lot more dispersed here with the same initial droplet density. You are seeing a lot more the confined, the clustering behavior, so seen in the high temperature. So how do we quantify that? I think we borrow the concept of the Voronoi analysis, which is basically the individual droplet particle is measured the V quantity, which is about distance to the nearest neighboring droplet. So this, well, long story short, this was a well-established conceptual picture, which is much better indicator than the random sample volume and counting the number of droplets inside the box. So the clustering index K is defined as such. So again, simply put, the large value of K means they are clustered. In the perfectly random distribution, Poisson distribution, K will be 1. And when K is less than 1, it means that they are widely dispersed. So you can clearly see that the highly dispersed pattern is observed in the center core region, and clustering is mainly done on the mixing layer zone. And not only that, but also the peak value of this clustering index is important. As you can see, the values are much larger when your droplet is faced against the hotter environment. And the physical reason for that is multiple aspects. It is due to the turbulence mixing and the drag induced by strong evaporation. So we are in the process of, I think, getting this paper published. I think more details can be found there. But again, the important message here is that the droplet, the flash boiling was not observed in any of these conditions. And the dispersion pattern changes with the surrounding heat, and more the pronounced clustering is observed when the ambient temperature gets hot. So those are the key characteristics of the droplet spray. Okay, so now moving on to the second topic, which is about turbulent combustion modeling. Now we are trying to deal with the ammonia. This time it's a gas phase turbulent combustion. My student Suleiman did most of the work here with the help of Francisco. So we have an in-house experimental capability of studying ammonia turbulent jet flames. So this is, we're talking about non-premixed jet flame here. This is a famous KAUST high pressure duct. So this is the entire duct is a 2-story tall, very long duct, which can be pressurized up to 40 bar. So you can include all the jet flame burner inside it with full optical access. So this is a specific jet burner configuration with this ID/OD specification. It's a small concentric jet through which we are providing some mixture of the ammonia and hydrogen with those ammonia cracking in mind. And those are the basic study. We have just launched the study, and some of the preliminary results are coming out. These are excellent topic for the next TNF workshop. We are already working on it. Now, so in order to predict that observed experimental configuration, we are also conducting large eddy simulation to match these results. So in doing so, again, DNS is not feasible. We are trying to develop some combustion submodels. And these are the two benchmark turbulent ammonia flames. And of course, the time averaged and the instantaneous snapshot image of TF1 and TF2. Those are the different crack ratio. So we have a little bit more hydrogen in TF2 than first case. And the Raman-Rayleigh scattering measurements were done at different stages downstream. The Reynolds number and all the parameters are given here, as you can see. And so here is a reproduction of this using OpenFOAM simulation. These are standard reacting foam with all the bells and whistles implemented, right? Of course, there are certain levels of combustion submodels available, but I believe my understanding is there are lots of the research groups in the world using OpenFOAM, same reacting foam, but everyone is using their own in-house submodels for combustion description. So this is another good area of collaborative research and kind of a friendly competition through the framework of a turbulent non-premix flame workshop. So here is a 3D structured mesh and about 4 million grid cells, and the specification exactly identical to the experimental burner. As before in the spray simulation, we have a straight pipe with the turbulence generation. So we have a fully developed turbulence coming out. And we try to reproduce the experimental data. Well, so this is a combustion simulation. The mechanism of ammonia mechanism is still a quite active research topic today by various kinetic developers. KAUST is also developing it in-house. We have Prof. Sarati group is doing that. So well, I don't mean to promote that our mechanism is the best. There are many other mechanisms that also gives a good prediction. As you can see, we have tried like 4 different mechanisms, including our in-house ones. They all predict the extinction temperature and strain rate fairly closely. So in that sense, there is not much of a difference. But although the recent KAUST mechanism published recently last year includes some additional updates in terms of hydrogen formation, I guess some of the main topic is again the additional chemical pathways associated with the hydrogen and ammonia, and then their contribution to the NOx formation as well. And also we are also looking at the pressure effect. So this particular flame experiment was done at 5 bar, and again high pressure, the kinetics at the high pressure condition is another subject of investigation. So we adapted the Zhang mechanism, and this is a standard bread and butter the flame net progress variable approach. And I don't think I need to talk much about it. This is standard technique with the both mixture fraction and progress variable as mapping variables. To include the turbulence effect, we do the presumed subfilter PDF to integrate those the cell averaged species and temperature and the density quantities. So these are built in just a similar way as many other people are doing. So this serves as a good benchmark submodel. But in terms of additional advanced model development, we took one extra step. Recently, we started developing into this principal component analysis, PCA, which is a kind of idea originated from Sutherland and Parente about decades ago. The idea is that if you have large enough flame data, if you align them through the scatter plot, you can find some two or maybe multiple, handful of those important principal directions, which is not necessarily a single component, but it's some linear combination of those. So those are the ideas. So instead of developing this PCA from complex turbulent flame simulator, which you can also do that, but we are just borrowing this machine learning ideas of generating a whole bunch of the strained laminar counterflow flames and at different strain conditions so that we can cover different phase space, the state vectors, and train them. So by this training, we come up with the principal components, and which may end up being a mixture fraction and progress variables in some cases, of course. And anyway, but these are agnostic, intuition-free generation of principal component. So the idea is this kind of vector matrix operation. So the reduction comes from solving for those total NS transport equation, as many as a number of species variables, reduced into the Q transport equation. Q is a number of principal components. So there's a huge amount of reduction in terms of transport equation being solved, and in the remaining species concentration is retrieved by this matrix inversion process. But on top of that, as I said earlier, we are utilizing machine learning to speed things up. So this is a so-called the PCDNN, a deep neural network algorithm, is being used to tabulate all these PCA analysis instead of computing on the fly. And in doing this, as our first step, the Lewis number effects, many of you in the audience knows about it. The unity Lewis number model was employed because general accounting for this non-unity Lewis number effect is complicated. There are not a unique single way to do it, and this is a subject of our future investigation. So long story short, we have tested it out and experimental data, and then we have compared the result from PCDNN, new model, versus old standard model of FPV. They look they are pretty good, and they look comparable. They are not exactly identical, but they both give good results. So comparing with the diagnostic experimental data, in terms of temperature, ammonia, hydrogen, all the prediction looks pretty good, and both PCDNN and FPP result yields nearly identical results, which is good. So we confirm that PCDNN works. The only exception is the hydrogen prediction is off for both model, but it's easily attributed to the unity Lewis number assumption. So this is some area of the future improvement. Having said that, it was actually remarkable to see that water prediction was still good, despite this unity Lewis number assumption. So this is actually different from typical hydrocarbon fuel. I guess because water is produced from ammonia combustion as well as hydrogen at the same time. So I think there's some offset effect by utilizing ammonia as a fuel. I don't know if you hear the noise. Actually, it is raining as we speak in here, so that the rain falls on in the building that is creating the background noise here. All right. So we also predict this is TF1 and both different flames. TF2, as you have a higher crack ratio as expected, hydrogen prediction gets the error increases because you have a large amount of hydrogen. We also try to measure and predict the NOx prediction, NO mass fraction, for example. Again, they are yielding a comparable accuracy between the two models. So at this point, this was found to be concluded to be acceptable, and with more work to be done. So local extinction behavior in terms of data scatter is also reasonably predicted. I can't say for sure which model works better here, but both are able to produce some of these local extinction event not as perfectly as experimental data plot, but they're pretty good. So those are the kind of work in progress. We are trying to develop the full-blown PCDNN based, which is actually a very powerful tool when it comes to the chemical behavior becomes highly complex. Okay, I think I left about 15-13 minutes of the time. So I'm gonna switch the gear, and the next topic of my OpenFOAM application is about spray simulation. This is non-reacting, but yet highly complicated physically and computationally intensive simulation. My student Alberto Cheskin has worked on the spray part, and Paolo Guida, he recently graduated. He worked on the droplet explosion problem. Well, so another kind of background on the intro material. So I guess the world is recognizing that liquid fuel will remain important even far into the future. So we still need to work on some kind of liquid fuel. It can be either hydrocarbon, fossil fuel based, or e-fuel based. But in the engine community, more recently, people are looking into the oxymethylene ether called OME, and there are different number 3 to 5. Those are considered very promising engine fuels in favor of the good NOx and soot characteristics. So those are, and they can be fairly easily produced from other biofuels and so on. So these are considered the other promising diesel substitute for the time being. So there is a growing interest in the engine community, such as Engine Combustion Network. People are doing some experiment for spray characterization of this OME3. So we conducted some high fidelity simulation. What is challenging is that this initial primary breakup behavior, in order to characterize the different injection strategy and how the injection strategies affect the subsequent soot and NOx prediction. So in doing so, really the initial primary breakup phenomena is extremely multi-scale, large spectrum of scales, and it is very, very difficult to reproduce. And experimentally, it is highly challenging because, again, as I said, the sheer dynamic range of the physical scale associated with this presence of the shock wave, compressibility effect, and extremely high velocity of the jet, and the dense regions and multiphase, it's such a nightmare. So it is experimentally very difficult to measure, although there are some limited amount of data available. And so we are trying to do the first principle simulation of that. In doing so, initial simulation, we neglect the cavitation behavior and evaporation and reactivity and multi-component. All those aspects are simplified. Still, it's a very complex problem. So it is a single, component, the single fluid model with the two-phase represented by volume fraction of the liquid, which is alpha L, and the alpha G is the 1 minus that. And we are solving for all the continuity momentum energy equation. And then advection of this, the volume fraction is also done through this VOF approach. So this VOF is already built-in function for, there is a module for OpenFOAM. One of our key major breakthrough in our endeavor into this interface phenomena was these piecewise linear interface calculation based use and then reconstructed distance function. This PLIC RDF is an acronym. So again, I don't want to dwell on too much on this methodology. It borrows from the recent publications in JCP. I think this picture gives us a clear idea about what this RDF is about. This distance from this cell, you construct the interface based on the volume fraction, and then pick up the normal distance as the reconstructed distance function. And capturing this behavior accurately is critical in the accuracy of the actual the surface breakup phenomena, which is relying heavily on surface tension. So this is found to be a lot more efficient compared to the conventional algebraic method. And the right picture tells us about actual numeric values of the distance function in each of these cells. And this is how we can actually implement. And the VOF simulation has been conducted. And combined with the AMR, this animation clearly gives us an idea of how that works. Again, we didn't invent it. It was also implemented in some of the OpenFOAM toolkits. So once again, demonstrating really the advantage of utilizing OpenFOAM. There are many tools already out there. We just need to borrow and add some more functionalities. So this is a nozzle geometry, slightly convergent nozzle. This is a standard ECN spray D with the OME3, with the nitrogen surroundings is a main study here. And we have very fine grid, about grid size about 1 to 2 microns, that to capture some of the smallest droplet that can be produced out of this jet. The breakup has been captured. Boundary conditions, we have two cases, case A and B. In terms of inlet liquid column, we use a flat velocity profile for simplicity, and then we also use is a turbulence using the same pipe flow geometry. And at the wall, we have no slip for the flat case and no slip condition for the turbulent case, to be realistic. And this is an inlet velocity history. Starting from 0, you are shooting it off, and you see how that develops. So first demonstration, I think this was quite an impressive large simulation costing multi-million CPU hours. And you can appreciate such a fine scale details of the droplet, small spherical droplets are being produced as the jet breaks up. This is a fairly challenging physical phenomena. And then you can really see the sphericity as a function of axial position. So you kind of appreciate the kind of child droplets and how they are formed and where. So these are the snapshot image comparison between the flat inlet versus turbulent inlet. Obviously, turbulent inlet tends to break up faster, showing a lot of these Kelvin-Helmholtz type breakup on the side of the liquid column is more pronounced. And we were able to capture some of the physical behavior that was observed by experiment. These are the shock wave associated with the liquid column hitting onto the nitrogen environment. We are forming the shock wave, and that actually contributes further into this breakup behavior. And those are clearly reproduced successfully by this high fidelity simulation. And again, I'm kind of repeating myself. Some of these are breakup pattern. These are some sketches of how they breaks up into small child droplets. And these are really captured by our simulation right here. And this actually confirms some of the similar features already found in the diesel spray experiment. So I think this was one of the rare high fidelity simulation, in my opinion, to our knowledge. This is one of the first success story of this DNS of reproducing the jet breakup behavior, liquid breakup, in a fairly faithful way. Okay, so the last topic, which was also kind of a cool demonstration, and I think this is again one of the first demonstration of this single droplet breakup, in particular associated with the bubble inside. And these are obviously quite of practical interest, especially when you're dealing with some heavy fuel. And in fact, at KAUST, we have ongoing activities of heavy fuel oil gasification. And this was one of the practical context. So people also did the experimental investigation of suspended droplet, how they break up when they heat it up, especially when there's tiny bubble inside. And these are highly complex phenomena. And experimentally, it is really limited. And suspended droplet, it only allows a large droplet, so you can't really measure small droplet behavior. Frame rate is, the resolutions are limited. And thermocouple, if you want to measure the temperature, thermocouple becomes intrusive, and so on. So there are many, many experimental limitations. Nevertheless, some experimental measurements have been attempted. And to our knowledge, there is no direct quantitative comparison of the behavior by simulation result. So we conducted that. So same type of, unlike the spray simulation I showed earlier, this time we actually did the multi-component. So there's a boiling and so there's two fields for energy and species. Individual multi-component species equations are actually solved. So those are the difference in this VOF application. So it is more computationally intensive, without reaction though at the moment. So the setup is the following. We have a single spherical droplet within which we have a certain shape of the spherical bubble inserted inside off center. And well, major approximations of microgravity. I think it's justifiable because considering the size of the droplet is tiny. And the thermocouple is neglected. So obviously there is an expected gap between the experimental data and simulation. So here is a picture. Here is a experimental behavior observation. You kind of see the hole forming here on one side due to the bubble, and there's a bubble burst of so that child droplet is ejected out. And this is a phenomena we wanted to reproduce. And this is a computational simulation and animation here. So you can see the exactly same phenomena was observed with the help of this presence of the bubble inside. You are having this the shoot out of the tiny droplet. So this was quite a triumph of our computational tool. Again, as I said, this click RDF algorithm was critical in capturing this intricate surface phenomena. And we further conducted quantitative, well, I should say qualitative at the moment. So quantitatively, there's still an error, but this was really the first demonstration that we were able to capture the size of the ejected satellite droplet is increasing as a function of alpha r, which is the diameter ratio. And we were able to reproduce that faithfully. And likewise, the surface area, the time at which surface area is maximum, again, we matched the experimental prediction fairly closely by the numerics. So at least a qualitative trend is well captured. This is another example, more recent study of doing the biojet fuel breakup behavior. You appreciate how they change qualitatively the breakup pattern, even with the same initial condition, depending on the surrounding pressure condition, the breakup changes significantly. So, and then again, we are comparing some of this observable behavior. So why does it matter? I mean, why do we do this? So as I said, we are developing this computational simulation module for HFO, the gasification tower. In doing so, there is an injection of the liquid droplets, and they will break up, and they need to be gasified. So we want to really have, this is such a complex phenomenon. We want to run like hundreds of these simulations, depending on the droplet size and bubble size and viscosity, density, and so on. And we will build up and also introduce some multiple bubbles. This was really a cool reproduction of the physics by having, and you kind of see that this tiny bubbles actually move around the surface and gets absorbed into the big droplet. So they don't really contribute much into the eventual droplet, child droplet formation. So anyhow, many of these simulation data is used to compile our characteristic time and some of those global quantities that are being useful in the engineering type of simulation. So we are in fact utilizing this correlation data to simplify the whole droplet tower simulation. And this is actually current work in progress. So I think that's good timing. I don't leave too much time for question, but anyway, that's a kind of a show off of our small snapshots of our ongoing projects utilizing OpenFOAM. There are a few others, but my time is limited. So I would like to just summarize by just concluding that, well, OpenFOAM is a really good versatile CFD that gives us many functions without each of the group, research group to invest into development. So such as flow solver, unstructured mesh, adaptive AMR, Lagrangian model, reaction, combustion submodels, all inclusive. Each user needs to tweak some of the weak areas, and then we can immediately get the results. So I think we are hoping that many of the audience here today have common framework, common platform of OpenFOAM. I think this is another benefit of working on OpenFOAM community to enhance easy collaborative programs between different groups. So with that, thank you very much for your attention. I'll be happy to answer any of your questions.
Okay, thank you, Professor Im, for the very intriguing and informative talk. We have now received one question and two actually now. The first one is from Ningyi Li. Hi, Professor Hong Yim. Thank you for your excellent presentation. I want to ask one question. You showed there is a local extinction of ammonia combustion in the simulation. Is there a special regime to capture the extinction and reignition phenomenon in the FPV method? Because it is a bit difficult to capture this in the flamelet method. Thank you.
I don't think this is new. Well, this is exactly the reason behind the flamelet model getting extended into flamelet progress variable approach, FPV. So FPV, by generating the entire S-curve in the tabulation scheme, it allows us to capture some of those quenched flamelets. So this is a general standard approach. We didn't do anything special here at the moment, and it is proven to work. Well, I must say it is not perfect, but as far as its standard turbulent jet flame, non-premix jet flames are concerned, I think FPV has been used extensively in the past, and that is what we are seeing as well. I hope did I answer your question?
I think the answer is yes. Okay. Yeah, let's go to the second question from Fan Zhang from Tianjin University. So he has three questions. The first one is, for the DNS case, do you generate initial turbulence in a pipe and let it fully develop? And how long is the pipe? So and the second, should I read it out or should I read one by one?
Well, I may ask you again. So let's hear that.
Yeah, let's do it one by one then. Yeah.
Oh, should I do one by one? Yeah. So pipe the length is 10 diameters, and it's the periodic pipe. So we keep it flow and until they are fully developed. And once it is done, and then we just bring them into the inlet. So that's how we do it. And this is Again, fairly standard technique, and we have been using it for many years.
Okay. The second question is, in this DNS case, since Droplet is modeled by Lagrangian particles, how many particles are there in the grid?
You mean the first topic, the ammonia spray?
I think that's what he meant.
Yeah. Well, I'll have to go back, ask my students about the exact data, but let's see. I don't know if I have the number here. Oops. Going back to the ammonia talk. Yeah. Well, so there was, about this first phase ammonia droplets. I don't have the exact number, I'm sorry, but I guess there are like several hundreds of, maybe if not thousands. Those are seeded into it's a monodisperse for now. The droplet radius is 6 microns at the same velocity as a flow, and then we are just injecting at the nozzle. Well,
Okay.
This is not about, this is still initially a fairly dispersed spray. So we are not really complicating the problem by allowing them to collide and merge. It is a single Lagrangian particle, and we are just each of them are evaporating, but we want to know how they disperse, and this dispersion pattern is a key subject in this study.
Okay. In fact, that is related to one of my own questions, so I may just ask now. So I can see the size of the droplet is so the diameter is 12 micron. And how does it compare to the mesh size near the inlet? Because it could be a problem when they become comparable.
You mean the jet breakup part here?
No, the so when
you mean the ammonia spray?
Yeah.
Well, so again, these are, we want to make sure, well, this was actually one of the questions by the reviewer of the paper. So, well, obviously the Lagrangian spray model, the validity is such that your droplet size must be sufficiently smaller than Kolmogorov eddies, as well as the cell size, and which is the case here. So that's my simple answer to that. So we have made sure the condition is met, so we can justify the use of that. Okay,
thank you. So his last question is, for the LES case, what is the advantage of your machine learning method compared to the others?
Well, again, machine learning is everywhere, as you know, and we are just also using them. Well, I didn't mean to, well, machine learning can be added to any submodel. In fact, we are also working on a standard FlameNet progress variable. Even tabulation can be done by machine learning. So you can tabulate it and look it up, and those tabulation algorithms can also be enhanced, accelerated by machine learning. So I would, again, my simple answer is that machine learning is a separate tool, and for whatever is just the fact that tabulation relies on big data, large number of data, and curve fit, and so on, and those are the usual target that can be easily accelerated by the use of ANN algorithm. So just to elaborate more, my new approach of this LES is based on PCA analysis. I guess the advantage there was clear. We are trying to reduce the number of transport equation being dealt in the LES simulation. Okay, thank you.
Okay. We have some questions from Huang Wei. Do you want to ask yourself, or should I read them for you?
Okay, I can ask myself. Okay.
Sure.
Yeah, thank you very much for your nice talk. Professor Im. So for the first application, so what is the carrier gas for the ammonia droplets in the jet? It's
What is what?
What is carrier gas? What is the composition for that? It's
Well, so these, sorry, I think it's just the nitrogen.
Oh, it is pure nitrogen, right?
Well, it really, yeah, there is no reaction whatsoever, and just the droplet evaporates. So this was not a environment was, no, sorry, composition is air. But it really doesn't matter. There is no reaction, and the density is all accounted for in a general way. So
okay,
yeah.
But for the gas phase inlet, it is ammonia plus missing, right? So here missing is gas, right? This is my question for the jet flow.
Yeah, this is a air jet and laden with the ammonia droplets.
But in your slides, the gas phase inlet, it is ammonia plus methane in slide 14.
Okay.
Yeah.
Oh, okay. Oh,
Yeah, so,
sorry.
Yeah, so it's a missing diffusion flame, right?
Yeah, again, I didn't pay much attention to that because we are not
Okay.
talking about the combustion phenomena here. This
Okay.
is mainly about single Lagrangian droplet evaporating, losing its mass until it evaporates. And through that evaporation, there's a mass momentum energy exchange with the surrounding gases.
Yeah.
So I apologize, maybe I made a mistake, but all those transport thermodynamic properties are kept as it is. We're just dealing with those mass heat exchange as shown right here, and this one, right?
Okay. So actually, there's a second question from following the first one. So how do the ammonia droplets affect the gases flame? So if we have the missing from the jet, because so originally we have the missing flame, right? Because the missing is from the jet, right? So it is a missing jet flame, right?
Mm-hmm.
Then we also have we injected the ammonia spray from
you're
the jet.
talking about so the dual fuel like ammonia added into the methane flame.
Yeah.
But yeah, so those I guess so that is a kind of a scenario you may kind of think about having a methane flame surrounding the ammonia spray, for example.
Okay.
And ammonia will provide those evaporative cooling to cool off the core region and so on, and then they will also be dispersed in such a manner. So these are kind of exactly the context of our study, right? At the moment, we only represent those effects of the heated surroundings by just heated air. So yeah,
okay,
without considering the combustion. So that's the future work to be done.
Okay, no problem. Yes, thank you. So my second question is for the VOF case. So when the droplets from the liquid breakup become smaller and smaller, so finally they will become subgrid, I guess, right?
That's
so
right.
So in your case, did you consider the transition from the, interface capturing to Lagrangian droplet checking?
Yeah, so we don't switch over to Lagrangian in this whole simulation, which becomes, well, that's the ELSA that engine people do.
Yeah.
Although their Eulerian version is much more crude. This is a really kind of extreme Eulerian simulation. We just resolve as much as we can, and beneath it, we ignore them. And anything droplets smaller than the size of the resolution, we ignore them. That's,
okay. Okay, I guess when because here is non-reactive, right? I guess when we consider the combustion case, then yes, okay.
So we are trying to get the extreme and the high fidelity and just push to the limit to see whether you can really reproduce this physics of the brake.
Okay.
That was the scope of this work.
Okay. Thank you very much. Yeah.
You can use it for actual engine simulation at the moment.
Yep. Okay. Yeah. Okay. So thank you.
Any other question?
Yes,
there-
there's one more from Dr.
Yeah.
Bolson Wang.
Yeah, I can read it too.
So okay, maybe I can read for the audience.
Yeah, so
okay.
his question was about flash boiling breakup regime. So this is one important area of interest. We originally was hoping to find anything similar. We were not able to find that scenario yet. So, well, to tell you the truth, I don't have a quick answer to you for that question. This is another topic that we want to identify. And we are not even sure whether in fact is a flash, how important this flash boiling is going to happen with the ammonia droplet in the practical, the combustor condition. So yeah, we are working on ammonia jet flame at the moment. That's the second question. I can read it. Does KAUST have a benchmark jet flame of ammonia methane with detailed measurement? Yes, answer is yes. Although we are not directly injecting ammonia spray, it is all the ammonia flame you have seen, right? So we have different types of fuel mixture. We have a blend of ammonia methane. And so those database will be generated and will be made available to the community through a TNF workshop and so on. So more will come out soon, and stay tuned. And you can feel free to contact me later if you are looking for some experimental data.
Okay. Right. I actually have a small question for that.
Sure.
So is that going to be this TF1 and TF2 ammonia flames? Are they going to be available for the next TNF workshop?
I think so. Yeah. You know, you probably didn't attend TNF this time. There was
No, I
a
didn't.
special an ammonia session within TNF, and we also talked about it. So this will be definitely a growing topic. Stay tuned within the community. You know, feel free to join those monthly meetings, and there will be more discussions about how we're gonna share the KAUST ammonia jet flame data.
Okay.
Definitely, it is coming. Yeah. Thank
Yeah,
you.
that sounds wonderful. I think a lot of groups will want to try to simulate like what we did for Sandia flames. Okay. I think that's all we have.
For everyone. All right.
Okay,
Thank you very much
again.
for sticking to the last minute. All right. I appreciate again your invitation. I had a great time.
It's great to have you. Okay.
Thank you very much, Prof.
Thank you.
Have a good flight tonight.
Yeah, have a good flight.